Hi, I'm Brian Goldblatt, and this is my object moving at constant velocity lab. So this was our experiment. The setup was an object that would be observed rolling across the screen. We had some assumptions to make, mainly being that the object was rolling on a flat surface, there was a constant center of mass of the object, the camera angle was straight on, and there was a constant velocity. We wanted to compare the position as a function of time using measured actual position in the video and a simulated predicted position. The main idea used in this experiment is Newton's second law, which gives a way to predict future velocity using velocity final equals velocity initial plus F net over mass times delta t. However, this experiment assumes constant velocity, meaning that F net is always zero because there is no change in velocity, which means that no forces are being applied. Since F net equals zero, final velocity equals initial velocity, and velocity initial can be obtained from tracker video analysis. And since F net equals zero, future position can be predicted using final position equals initial position plus velocity times delta t. And the result of this experiment is that we saw that constant velocity is more theoretical than practical in most cases because it doesn't account for real-world forces. You can pause to look at the recorded data that I have here, and this is the simulation code that I had to run the prediction data. Here's the velocity vector, and as you can see, the Fnet is a zero vector. This is the simulation running in Glow script. It's very simple, it's just the ball moving to the right. So this is the graph of the velocity found using the first two increments of position and tracker. Using position update formula covered previously with the calculated velocity, the position can be predicted using our simulation and compared against the actual position in tracker. The predicted position diverges from the actual position and ends up being an overestimation due to certain external factors that I'll cover later, but the velocity ended up being 0.396 meters per second. Now when you use the final two increments of position to find the velocity, the predicted position ends up diverging from the actual position and is an underestimation due again to external factors that I'll cover in a second. But from the last two increments, the velocity ends up being 0.333 meters per second, which is a significant decrease from the first two increments. So why does the first two increments versus the last two increments create such a different velocity for our lab? So the fault that we made with our experiment is that the assumptions that we made in the beginning are all contributing factors to why the two velocities of the first two increments and last two increments are so different. The bottle was not really rolling at a constant velocity, meaning that other forces like friction were acting on the object. The table may not have been a flat surface, which would make the weight of the object be a relevant force. And I'm unfamiliar with the physics behind this, but the water in the bottle rolling as the bottle was rolling may have contributed to a changing center of mass while the bottle was rolling, which would most likely affect the velocity. And there was also probably user error in estimating the center of mass in tracker. Also, the camera angle may not have been straight on, and that would give the illusion that the water bottle was covering less distance than it actually was on the camera. In conclusion, we found that in an experiment where calculations compound on each other, slight differences in initial velocity would make a large impact on the results. What if the x-axis was flipped? Using the final two increments for the velocity with a flipped x-axis, the velocity is now negative 0.333 meters per second, which makes the position decrease as time increases. The magnitude of distance traveled is the same, and it's at the same speed, it's just going in the negative direction. How is there a zero net force? Assuming constant velocity, so force of friction doesn't matter, Newton's third law states that there's an equal and opposite reaction for every force applied. There is the force of the object's weight being applied down on the table, and the table is exerting an equal and opposite force on the bottle that is called the normal force. These two forces cancel out to create a zero net force scenario. There is no force being applied to push the bottle in the x direction because that force was applied before tracker began tracking the bottle. The bottle is moving as a result of that force, but it is not actively pushing the bottle. What if Fnet is not zero? A model of friction here presents the action with the motion moving in the right direction and friction acting on the ball in the left direction. Friction in the model prediction here is 0.05 newtons in the left direction, which is an overestimation of the frictional force in this experiment, seeing as the predicted data deviates from the actual data point significantly at around 0.766 seconds. Regardless, friction is still present here. It is just in a lesser quantity than 0.05 newtons. And here is the glow script code showing that now the velocity vector is 0.05 newtons in the left direction. Thank you for watching.